Hi everyone. So we're going to start going through the first lecture presentation for the course. This was already posted on Blackboard. You should have been able to download it and look through it. But we're going to go over it now in part. We'll try to do most of it and finish it up in later videos. Okay, so let's get started. So this is EPS 38, Introduction to Earth Sciences. The first lecture covering the first chapter. The textbook for the course is Earth Portrait of a Planet from Stephen Marshak. I told you that you can get any edition that you want. They're currently on the 6th edition. You should already have it by now. If you don't have it already, you need to order it immediately so you can get started. You should be reading the textbook before we talk about the material in these presentations. So make sure you've already gone through the textbook and don't just expect the lecture to cover everything that's in the textbook. Okay, so geology is the study of the Earth. Geo is a Greek word meaning Earth. So it's the study of everything that happens on our planet, right? So not just the rocks, but also the atmosphere, the oceans, and the interactions between them. Right, so the planet is, or Earth sciences is made up of study of things on land, including rocks, how they're changed, how they're made, how they're deformed over time, the oceans and the atmosphere. And the Earth sciences are also sometimes called the geosciences, and so they're made up appropriately of the atmospheric sciences, oceanography, and geology. So they're all different fields that all together make up the Earth sciences. So the Earth's surface is a very complex system with many parts that interact with each other. So here's an example of interaction between the interior of the Earth and the atmosphere, right? We have a volcanic eruption emitting gas into the atmosphere, changing the composition of the atmosphere. And so a volcanic eruption might be a single event that temporarily changes the local atmosphere, or the history, throughout the history of the Earth, changes in the amount of volcanism can strongly change the composition of the atmosphere itself. So Earth's atmosphere originally formed from outgassing of materials from the interior. So basically the rock that is makes up the interior of the Earth changed and emitted the molecules and materials that now make up the atmosphere that we breathe in. So everything was brought here first as. Here's an example of an interaction between the land and ocean. So we have rivers carrying sediments, which are just broken up particles of rocks into the ocean. And we have waves eroding and breaking down rocks on the beach, right? So another interaction between the water on the planet and the land surfaces. So the Earth itself has a interior diameter of around 6,370 kilometers, or almost 4,000 miles. So I don't expect you to remember that. I'm not going to give you an exam that asks you how, what is the mean radius, not mean diameter, actually, mean radius of the Earth, how deep is the Earth, or anything like that. But around 4,000 miles is kind of a nice number to remember for that, just to have in your head. So the atmosphere is around 100 kilometers, and that would be about 1.5% of the thickness of the radius of the Earth. The atmosphere is a very thin shell around the rocky Earth. The breathable part of the atmosphere is only around 8 kilometers. That's 1/10% of the thickness of the radius of the Earth. So the atmosphere extends far out into space, includes parts that we don't really come into contact with. The oceans are around 10 or 11 kilometers deep, and so that's again around 0.1%, 1/10% thickness relative to the radius of the Earth itself. So everything that happens on the surface of the Earth, down to the bottom of the oceans, up to the top of the atmosphere is only a few percent, right? It makes relative to the rest of the rocky planet. So it's a very thin veneer around everything. And the rocky part of the Earth is the remainder, around 99%. So most of the Earth is a solid material made up of rock. The Earth is a planet. I hope that doesn't surprise anyone. The planetary science, so Earth sciences are one of the planetary sciences. Our solar system is made up of lots of planets, including Mercury, Venus, Earth, Mars. Those are the rocky planets. Jupiter, Saturn, Uranus, Neptune. Those are the gas giant planets. And no longer Pluto. This is an older graphic from a while ago. Pluto is now excluded, or not considered a planet anymore. That's because we found objects that were the same size or actually even bigger than Pluto. and so we'd have to start including them among the planets. So rather than preventing all this chaos, we ruled them out. And this is kind of a nice thing, actually. So most of my life, Pluto was a planet, but now it is considered not to be. And so kind of the point here is that even some very basic facts about our world change, or at least our understanding of those facts changes over time. So even the best scientists have had to change their minds about things, and that's fine. It causes some confusion for some people, but that's reality, right? It's good to be able to change things. So here's a graphic showing the planets and their relative sizes. So the sun is much larger than any planet. Obviously, it's about 99% of what makes up the solar system. Mercury is a very small planet. Venus, Earth, and Mars. Venus and Earth are almost the exact same size. Mars is quite smaller. And then Jupiter and Saturn are the largest planets, and even Uranus and Neptune are gas giants compared to things like Earth. And Pluto is also very small. Okay, so I think I said this before. We have the terrestrial rocky planets and the gas and ice giant planets. Here's a chart showing the relative distances of the planets, the terrestrial planets from the sun. So here is, this dot represents the sun. This green circle represents the orbit of Earth. And we call the distance between Earth and the sun 1 astronomical unit. So we've just invented that up. We invented that and because we like to think about things relative to the Earth. And so it's just a made-up unit of distance. And so now this, moving outwards from the sun, we have Mercury, Venus, and Earth, and then Mars. And Mars is about 1.5 astronomical units from the sun. So 1 astronomical unit is the average distance from Earth to the sun. It's around 93 million miles, close to 100 million miles, right? It's not, again, going to ask you to remember that it's 93 versus 100 million miles. Kind of 100 would be kind of a good number to have in your head for that distance. Or that astronomical unit could also be 150 million kilometers. Okay, now moving out further, we move out from now Mercury, Earth, Venus, Earth, Mars to Jupiter. Jupiter is 5.2 astronomical units away from the sun, right? So it's 5 times as far from the sun as Earth is. And intervening between Mars and Jupiter is the asteroid belt, which is made up of many small rocky bodies. These are the rocky bodies that are leftover remnants from the formation of the planets. They were formed very early in the solar system. They're actually older, or many of them are older than the planets themselves. Okay, now moving further out, we have the Sun and Jupiter. Now you move out to Saturn, move out to Uranus, which is very far out in space, and now to Neptune at 30 astronomical units away from the sun. So 30 times further from the sun than the Earth is from the sun also. So we have a lot of different objects in our solar system. We have the planets, which we just talked about. We have moons, we have asteroids, we have comets, we have all kinds of objects and bodies in the solar system, right? So the inner planets, the moons of the different planets, and the asteroids are all rocky bodies, whereas the outer planets and things like comets are made up of gases and ice. So there's 2 main big divisions in composition for things in the solar system, right? Is it rocky, or is it made up of gas, ice, and dust? So the planetary sciences, of which the Earth sciences is one, look at a lot of different objects and things in our solar system. So we might have people that work on lunar geology, the geology of Mars, the study of meteorites, which is called meteoritics, not meteorology. That would be the study of weather, and lots of other different fields of science that make up planetary sciences. So our department is a department that's focused on the study of the Earth as one of the planetary sciences. Okay, so the sun is a star, and here's a picture of it, or an image of it. And that star is in the Milky Way Galaxy. That's our galaxy, and there's more than 100 billion stars in our galaxy. The Milky Way Galaxy is a spiral type of galaxy. This is not a picture of it, right? We can't see it because we're in the middle of it, or we're within it anyway. So our sun is around 24,000 light years from the center of the Milky Way Galaxy. And a light year is a distance that light travels in 1 year, which is around 186,000 miles a second. 1 light year equals 6 trillion miles, or 9.5 trillion kilometers, so close to 10 trillion kilometers. That's how far a beam of light will travel in a year. So the planetary sciences now, which includes the earth sciences, lunar geology, the comparative planetology, right? That is a subsection, a subfield of the science of astronomy. So in astronomy, you might study stars, the life cycle of stars, and what's going on in different galaxies, how they're moving, how they're interacting with one another. You can also study nebula, which are large clouds of interstellar and sometimes intergalactic dust that are the places where stars are starting to form. And so astronomy itself is a subscience of cosmology, which is the study of the whole universe, of all matter, time, space, and energy. So we're mostly focused on the geology of the Earth for this course. We'll talk about oceanography, climate, the atmosphere, the history of the Earth, the development of the Earth over time. So that's all of the Earth sciences, which again is part of the planetary sciences, subsection of astronomy, and all of that is just subsumed under cosmology. That's where you are in terms of the sciences. So now going in the other direction, we can start breaking up the science of geology into a number of fields, like petrology, which is the study of where we study rocks by looking at the rock themselves. We can also do mineralogy, where we're studying the minerals that make up rocks. You might study volcanology or work in that field, or seismology, where you're studying waves moving through the Earth. There are also a lot of people that work in plate tectonics, the movement of the plates that make up the surface of the Earth, and lots of different types of geology that are out. Right, so here's some things that you might look at when you're working in petrology. We have some rocks that are about the size of hand samples. You might study them that way in a hand sample. This is a formation of rocks that you might approach and study at the level of a formation instead of looking at the individual rocks themselves. And here we have a section of rock that's been cut very thin, thinner than a piece of paper, and we're studying it over a microscope. And we can study the different minerals and crystals that make it up. So here, each one of these different shapes here are different crystals that are different minerals. So these minerals make up perhaps these rocks, which are found in these large formations. So in mineralogy, you might look at not the rocks, but you might break up the rock and pull out the individual minerals that make it up, and then you can look at you can identify the minerals by looking at their crystal shape or their color or other properties that they have, and that can tell you a lot about the history of the rock and how it was formed. So certain minerals only form under certain conditions. So we can learn about the conditions that the rock experienced by looking at those minerals, way of reading the rocks. There's also geochemistry and geochronology, the study of the chemistry of the rocks. We might break them down into their individual chemicals and try to understand them, look at different isotopes that are in them. Or we might get at time, geochronology, through a type of geochemistry. And that can involve a lot of lab work using modern chemical processes. Volcanology is another subdivision of geology where people are studying the activity of volcanoes, the history of those volcanoes, and if there is an eruption, then they might even sample some of the material that comes out of them, what happens to that material as it's spewed out from the volcano, and they can classify volcanoes into different types and learn a lot about them through that. Plate tectonics is another subdivision of geology. So here we have the surface of the Earth, and it's broken up into not continents, but plates. And the plates are made up of continental material and oceanic material. And the plates have boundaries between them, which is what's shown here. And the plates are mobile. They move around. They move around relative to each other. And in fact, sometimes the plates grow and some of the plates shrink. So plate tectonics is a really important part of geology. It explains a lot of the major features of the Earth. So we'll talk about that in quite a bit of that. So geophysics or seismology, people that work in that field, which is a very wide field, they're looking at waves produced by earthquakes or waves produced by machines such as penetrating radar, or they used to use set off explosives to produce waves that would move through the Earth. And depending on the material that's present, these waves can move differently through that material. And so when they look at the different timings of the waves to show up at different stations, so they would maybe have a place where a sound is made and then a place where a sound is recorded, or several places where it's recorded. They can interpret differences in the material that these sounds have passed through based on when and where they show up at their recording stations. So this is also, most often done for earthquakes, right? It's how we pinpoint the position, depth, and strength of earthquakes using seismometer stations all around the world. And there's also a subdivision of geology called stratigraphy, where we're looking at the different strata or layers of rock. So in something like that, you wouldn't necessarily have a hand sample or a microscope that you're concerned with. You're trying to explain the presentation of these different rock strata. So you're explaining things on a higher level, a larger level than you would with, say, mineralogy itself. So again, from cosmology to astronomy, down to planetary sciences, earth sciences, and the geology of the Earth. So what is science, and what do scientists do, right? There's lots of popular depictions of scientists, and here we have the Frankenstein and his monster. And the idea there is usually that scientists are manipulating the world around them, right? So for the Frankenstein's monster represents the world. He has been manipulated and changed by the scientist. But that's not really what scientists do. And this is a more modern version of that story. So in movies and popular culture, that's how science is often presented. And even in things like the newspapers or media, scientists are shown in a similar way, especially about things that people are concerned about or that people are fearful of, like nuclear power or nuclear weapons, genetic manipulation, vaccines, all of that kind of stuff. But science is not seeking to manipulate nature. We might have to do things to natural objects in order to understand them, but we're not trying. The end result of science is not a manipulated version of nature. It's trying to understand nature. We want to understand and explain the world around us, the natural world. And scientists try to do that by the use of observations, experiments, and calculations to understand the world around us. So this is also kind of a cartoon version of that we're all probably pretty familiar with, starting in high school, of the scientific method, where you have observations, experiments, failures that you would then repeat, and then you repeat your observations and make new experiments based on that, right? Yeah, so identifying the problem, collecting data, proposing hypotheses, testing your hypotheses, and then magically, if your hypothesis is successful, it becomes a theory, right? So that's a very, like I said, cartoon version of what's going on. Hypotheses do not somehow graduate or grow into theories in reality. A theory is really just a hypothesis, an idea, an explanation that has been around for a very long time. And that hasn't been rejected for a long time. And so we just transition from this word of hypothesis to theory, based on social idea that this theory has been around for a long enough time to call it that. But overall, it's a pretty good start at how scientists do things. And you can compare it to how other types of people that try to understand the world around them do things. There's a really simple example where you go into a scientific method. You go into a bank one morning to get some money. The bank should be open, but you get there and it's closed. Well, why? So let's try that scientific method. Right? So we're probably not going to use any particle accelerators or chemistry to do anything about this, right? But we have a problem, right? The problem is that the bank is closed, and we want to know why, right? We have a question that we're trying to ask or trying to explain. So we can quickly collect some data, such as it's Monday, it says 9:10 on your watch. The bank hours are Monday to Friday, 9 to 5. It's very cold. There's people all over the place. So a couple hypotheses: my watch is fast, right? My instrumentation, the things that I use to gather data, are wrong. Or it's a holiday, right? There's just some other explanation to what things are. So if my watch is fast, right? One hypothesis is that my watch is fast, and if this hypothesis is correct, then another clock will say that it's 9 o'clock. So I check, or around that time, right? So I check a clock nearby, and it says it's around 9:12, right? So the hypothesis now has failed. we made an if-then statement, right? Something that follows from my hypothesis, right? And it's something that we can then verify, right? Or that we can rather check. And if our hypothesis implies something, and that something doesn't work out, then our hypothesis should be rejected, right? If this hypothesis is correct, then another clock will say that. If the clock doesn't say that, we can't keep that hypothesis anymore, right? We can kind of escape this by saying, well, the clock tower is also running fast, just as fast as my watch, and so I need to look for another place. And we can check 100 different clocks, and we can probably keep saying that and kind of do that forever. But eventually, people will, and ourselves should kind of catch on that this hypothesis that we liked in the beginning is maybe not really correct. Okay, so another hypothesis would be that it's a holiday, and therefore the bank is closed. So if this hypothesis is correct, then there should be no people around, and the post office should be closed, right? Maybe those are some reasonable assumptions, right? But there are lots of people, right? And the post office is open. So now we need to test our hypothesis, make some more observations, and feed back into this idea, scientific method. So this hypothesis failed because the observations don't match what it's connected to. So now we have to go back to our original, we've run out of hypotheses, we have to go back and propose some more hypotheses. So here's a new hypothesis, right? The pipes froze inside the bank and burst, causing the building to be shut down, which is very specific and very particular, and it's probably not what you would go to as a first hypothesis, right? It's very rare that something like that would happen, but much more common that your watch would be off, that a bank holiday would be occurring. So if this hypothesis is correct, then there should be some repairmen coming, right? And as you're thinking this, a plumber's truck shows up to fix these pipes, and we maybe even see them with pipe fixing equipment and going into the closed bank. So now our theory that the pipes froze and burst is successful in that the things it predicted bared out. It was not falsified. So our theory, or rather a hypothesis, if this happens long enough, for a long enough time, and there's no set number on how long it can happen, it's just an agreement between people, the language on it will shift from hypothesis to theory. So something like that happens in the scientific method, right? But we don't actually ever really confirm it, because maybe the plumber's truck that shows up is there for another building, or maybe the plumber is also looking for the bank and he wants to pick up a check or something like that. So there's always potentially something else that could falsify our hypothesis. Okay, so here's a geological example of this scientific way of thinking. So we're in this area, and most of the rocks look like this, right? They're kind of pink or salmon colored with some darker minerals within it. And the hills and everything around you are made up of that. But then you come across one rock that looks like this, and it's very gray, very dark, called a mafic rock with mafic minerals, and has these bright green crystals, or dark green crystals, right? Strongly green crystals. Very different from the other rocks. So now we've importantly identified a problem, right? What is the dark rock and how did it get here? Now, if we don't care about it, if we just see the dark rock and don't think about it at all, then we don't even identify a problem in the first place. And the whole system that we talk about with the scientific method doesn't even start getting applied, right? So identifying the problem is actually the biggest step in the scientific method, right? Or any kind of scientific investigation. For something like, why is my bank closed? It's pretty obvious what the problem is. Or if you trip over some black rock or in a place where every rock is pink, why is there a black rock here? That's kind of an obvious problem. But usually the problems are not obvious at all. And the questions that we want to ask are not obvious at all. Okay, so once we have identified the problem, we then make observations, right? We collect data, right? So we don't just look around at watches and clocks, but we might study the mineralogy of these rocks. We might study their chemical composition. We have to dissolve some of them, break them down. We have to collect them and bring them back to a lab. So the mineralogy of the pink rock, of the rocks, could be quite different. So perhaps the pink rock is made up of quartz, albite, and orthoclase, which are all light-colored minerals, felsic minerals. And the dark rock is made of olivine, pyroxene, and anorthite, some mafic minerals, right? So different large-scale features And when we look at a smaller scale using a microscope, we see some different materials making them up. And then when we start breaking down these minerals, we can look at the chemistry of those minerals themselves, right? So the pink rock, the minerals in them are high in silicon, potassium, and sodium, low in iron, magnesium, and calcium. And the dark rock is rather different, almost the opposite, really. It's low in silicon, potassium, and sodium, and high in iron, magnesium, and calcium. Right, so different chemical compositions, different elements make them up. So the pink rock is a type of granite, and the dark rock is a type of basalt. So now we've actually gone from mineralogy, right, to petrology. We've had to use two different fields of science, right? We use mineralogy to look at the minerals that are present, to assess them, did some geochemistry to look at the elements that are present, and then we use the science of petrology to then identify them not merely as a list of chemicals, but as a type of rock called granite and a type of rock called basalt and all the things that they mean with them. So the different fields of science are important, and they actually give us a framework in which to think about these things. Okay, so now we can start proposing some hypotheses. Perhaps the basalt was ejected from a volcano and landed here, or it was carried here by a glacier, or the basalt came from a layer higher up on the mountains, or the basalt is a meteorite. People look at those kind of rocks and think, oh, this could easily be a meteorite, right? It kind of has that look. Very common idea for people. So now we test those hypotheses. It was ejected from a volcano. Well, if this is correct, there should be a volcano nearby. And we look around and there is no volcano. So there's no volcano for this to have come from, right? So it didn't get here because of a volcano, right? At least not immediately. So that hypothesis fails, right? We had something about that hypothesis that we could check and was falsifiable. But then it was able to be checked, right? Not just any kind of idea. Okay, so the rock could have been carried here by a glacier. Well, if this is correct, then there should be some glacial landforms around us. So notice we often have this structure of these if-then statements. And it was, so like I said before, it was very important to just identify the original problem in question. Now, once we have some hypotheses, we have to also then identify this then statement. What are the things that are connected to it, right, that are falsifiable in order for us to test that hypothesis, right? We want for hypotheses to go through the hardest test possible, right? We don't want them to be tested by something very simple or easy that they can easily pass. It's better to eliminate hypotheses. We want to eliminate them so we can move on to better alternative hypotheses that might actually be true. Right, so we make some observations, and the mountains and canyons here have been carved by not ice or not glaciers, but water. So this hypothesis failed. It was not transported by a glacier, at least, because there's no glacial indications here. The things that glaciers make are not found, meaning there were no glaciers. Not just that we haven't found it or don't want to look for it. We can also, we had our other hypothesis where this rock came from a higher layer of basalt here. So if this is correct, then you should be able to find that layer somewhere, right? You might have to go up to the top of the hills that are there, and you might see, well, there's no basalt up here. But perhaps they were eroded away, right? Perhaps they wore away in that particular location. Then you have to be able to go somewhere else and find that basalt layer. And so until you find it, you really can't say that it came from some imaginary layer, right? You have to test for the presence of that layer. So here's our mountains in the original picture. And we go up there and there is no basalt, but like I said, it could have been eroded away. This hypothesis is unlikely since we can't find the basalt layer, right? So now we have to go back and maybe do some different alternative hypotheses. And so scientists work with multiple testable, right, something that can be falsified, something that can be shown to be false hypotheses. And often people have in their heads multiple competing hypotheses that are rather different. If one is true, then the other one is not. But so in science, the testable part is not simply that something should be proven true, right? What we really are doing when we're doing science is we're proving something false. And once it's proven false, we move on. And we never actually prove anything to be true. So this kind of goes on forever. You never really it's not that a hypothesis, when it's proven to be true, becomes a theory, for example. If something is true, then it's a fact. It's an observational fact, right? And hypotheses and theories never become facts. So some untestable hypotheses, right? A magician made this rock appear here, right? There's that could be true, right? Someone could have, who knows, right? But there's no way for us to even get at that. There's no way for us to test it. Or it could be that another geologist had picked it up at another site and dropped it here out of his pocket, right? It could be true. Certainly does happen, right? We know stuff like that happens where people carry objects and things from one place to another and randomly leave them. But there's no way for us to test it. So it's inaccessible in a way to science, even if it's true. Another hypothesis of ours was that this is a meteorite. Well, if it's a meteorite, then it should look like meteorites in a lot of ways. And one of the ways that we can kind of pinpoint something as being a meteorite is we can look at its oxygen isotopic composition. And so this is a thing that you do in geochemistry. And the oxygen isotopes have different ratios in different objects, and it tends to be that things that are formed on Earth have one ratio and things that are formed in space have a different ratio. So a space-like ratio of these isotopes, right, is a signal that the object came from space. And so when we test our rock sample, our basalt, we see that its oxygen is different from that on Earth. And it has this space-like signal. So our hypothesis is successful. Does that mean it's a meteorite? No, it does not mean it at all. It just means that we have not falsified our hypothesis yet. So now we have to think of some new tests for this, some new ways to disprove it. So we always test our theories against new observations. Maybe someone else finds that the sulfur isotopes of objects in space are very different from objects on Earth. But then we would immediately say, well, now let's take this new idea, let's apply it to our basalt rock, and let's see if it also, if it matches the space signal or not. So we would keep doing that. And perhaps it wouldn't match the space sulfur signal, and which would disprove that it came from space. Okay? So now, in this little imaginary example, a few years later, another meteorite is seen to fall, and when it's recovered, turns out to look exactly like your basalt rock, right? The minerals are the same, the shapes of the minerals are the same, the percentage of the olivine to an orthite is the same, and the isotopic compositions are all the same. So now you have some new observations that support your theory, which is nice, right? It's good. It doesn't necessarily make your theory true. Well, it certainly doesn't make it true, but it doesn't necessarily make it more true, right? It's just very supportive of your theory. So scientific theory is simply a hypothesis that has been tested and not failed so far. Theories can never be proven. They do not turn into facts. Theories can only be disproven, and then they have to be abandoned. So the only thing that we can do with the theory is get rid of it. Right? We keep them only temporarily. You're always trying to get rid of them. So science is the use of observation and experiments and calculations to learn how nature operates. Science is not just a listing or set of facts, right? People, so a lot of the basic facts about the world around us haven't changed, right? People 500 years ago knew what the world looked like almost as well as we do today, let's say. The facts did not change. But our understanding of those processes and how they, of those objects and how they were formed by different processes is what has changed. So science is a process, an ongoing process through which we change our understanding of the world. Okay, so with that, we'll stop and we'll cover some more material in some new lectures, okay? Okay, thanks.